So this video is in support of the numerical integration lab that you're going to be working on in Maple. When you have integrals such as these that look innocent enough but traditional techniques fail, then we turn to numerical methods using software to be able to get an approximation for the integral. And these are typically known as numerical methods, but in the end they produce an approximation. Whenever you see the word approximation, you should also think error. Right? If you're approximating something, then there's going to be a certain amount of error that's going to arise. These numerical methods are basically relying on the same principles as Riemann sums, where you're using a partitioning method. So let's do a quick little summary on the error analysis that you'll do for the lab. You're going to basically be computing the absolute errors. We're not going to worry about the relative error. But I wanted to make sure you understood the different kinds of error. So absolute error is when you take the calculated value, the absolute value of the calculated value minus the exact value, and the relative error is the calculated value minus the exact value, and then normalized or divided by the absolute value of the exact value. So I will ask you to compute the errors incurred using the three techniques that I'm going to show in this video. The first, there's basically three methods of numerical integration that we're going to touch on. The first is the midpoint rule, and that's really should be secondhand to you because it's really a midpoint Riemann sum. And the second is the trapezoid rule, and lastly is Simpson's rule. So the midpoint rule is basically, like I said, a Riemann sum where we're using rectangles and you're slicing up or partitioning into subintervals, and then you're finding the area of all the rectangles and then summing them up together. But you're going to use the midpoint of the rectangle as the length of the rectangle. So looking at the curve f of x, if you partition it into n subintervals, your width of the intervals is going to be found by subtracting, just as we did with Riemann sums, b minus a divided by n. So that's the width, delta x, of your subinterval. The height of it at the midpoint is found by calculating the midpoint of the interval, which is just x of k minus 1 plus x of k and divided by 2. And then the length of that is found by putting that midpoint into the function. So here's your length and here's your width. Multiplying the two together gives you an area for that rectangle, and then you're going to sum them. So let's look at the formal definition of the midpoint rule. It's usually denoted by m of n, and that's basically an approximation of the integral from a to b of some function. And again, the rule is using the midpoint of the subintervals. You're finding the height of that rectangle, and then you're multiplying it by the width. So it's basically, give you an idea here, right? You're using equally spaced subintervals. So again, delta x is equal to b minus a over n, and the midpoint. So you've got a sum of, and we're going to let x of k be the variable we sum over, times delta x. I'm running off the screen here. Okay, let me try and squeeze that in a little better. So that's times delta x. And adding that up gives you an approximation for the area under the curve. So just as in Riemann sums, as the number of subintervals increases, the approximation is going to improve. Okay, so at the completion of this video, I think I'm going to do a separate video where we look at simply one integral, and we'll try the three methods of numerical integration so you get a feel for mechanically how it's done. So the trapezoid method, or the trapezoid rule, relies on the same partition method, but instead of summing areas of rectangles, we're going to sum area of trapezoids. So here's your trapezoid, and hopefully you recall that the area of a trapezoid is 1/2 the two bases added together times the height. So in our case, in terms of the function, the area of a single trapezoid, and I'll just abbreviate it, is going to be equal to 1/2 f of x of k minus 1 plus f of x of k, and then delta x would be that height. So the trapezoid rule is denoted T of n, and that's going to just be equal to the sum of the areas of the trapezoids. Just abbreviate it here so you don't get lost. Okay? And that's simply what it is, isn't it? Exactly the same situation as with the midpoint rule. As n increases, the approximation is going to improve. So let me give you the rule for the trapezoid. And right here is your rule. And to arrive at that, it's just basically an algebra manipulation, and you end up with this rule for the trapezoid method, which is 1/2 f of x0, where x0 is where your subinterval starts, or your interval of integration starts, and then your last term, xn, is equal to b. And again, delta x is b minus a over n, and as n increases, your approximation is going to improve. So here is the trapezoid rule. If you are working these methods by hand, it's helpful to have a shortcut rule, and that's really addressed here at the end of this slide. If you know the trapezoid rule for n and m, the midpoint rule for n, then you can find the approximation for the trapezoid of 2 times n. So it would rely on, this formula basically relies on you having the midpoint rule computed and some values of n for the trapezoid rule. And we'll see this in action as well. So the last rule is the Simpson's rule. And with Simpson's rule, instead of line segments used with the midpoint rule and the trapezoid rule, we're going to use parabolas, which are defined by 3 points. For the Simpson's rule, you must have an n that is even. So n must be even in order for you to use Simpson's rule. And it gives a very good approximation. And you'll see in the example just how easy it is to hone in quickly using Simpson's rule. Now, the rule itself, you really do need to recognize a pattern. So this is, right, you're approximating with Simpsons of n. So the rule for Simpsons is right here. And you'll notice that your coefficients, you start out with f of a. So let me kind of just paraphrase it a little bit here for you. This is really f of a for the first point. And then it's for f of x1 plus 2, f of x2 plus 4. And you're going to see an alternating between these coefficients. So these coefficients are going to alternate 4, 2, 4, 2, on out. And that entire quantity is going to be multiplied by delta x over 3. So that's the Simpson's rule. It's much easier to find the trapezoid rule than apply the Simpson rule, which is more accurate. And we do that through this formula. So just like we had a shortcut for the trapezoid rule that was dependent on prior trapezoid rules and the midpoint rule. The Simpson's rule can be found strictly from the trapezoid rule. And the last thing for this video that I'd like to touch on is just some relationships for as far as errors in numerical integration. For the midpoint and the trapezoid rule, if you reduce delta x by a factor of 2, the errors are going to decrease by a factor of 4. So what that's really saying is that they're proportional to delta x squared. And for Simpson's, if you reduce delta x by a factor of 2, the errors are going to decrease by a factor of 16. So that is proportional to delta x to the 4th. Right? So let me just quick summarize that. You're going to reduce delta x by a factor of 2, and that is going to result in the errors decreasing by a factor of 4. I apologize, my stylus broke tonight. I'm back on my old one. It's not quite as crisp. And again, for Simpson's, you reduce delta x by a factor of 2, and because it's proportional to delta x to the 4th, it's going to reduce the errors by a factor of 16. Alright, so that's it for pre-exposure for the lab. I'm going to create another video which basically looks at one definite integral, and we'll take a look at each of the 3 numerical methods to solving that.